Hi guys, this is me Nitin, and in this video we are going to talk about Pytorch Metric Learning. So now if you're not familiar with what metric learning is all about, let me give you an example. So let's take apples and oranges. You can label the apples as 1 and the oranges as 2. Now if you do the same labeling on boxes and then store them somewhere, you can match and if someone does not knows what apples look like, they can see the label on the apple, that is 2, and then they can go into the warehouse and then they can see the same label on the box and they can identify like this box contains apples. So in a way the intuition is that based on the image there should be some quantifying vectors which can be used to compare the images to get the labels or get similar images. So metric learning is all about getting some n-dimensional vectors. So we will basically, in simple terms, we will train some model and then pass in an image. The model should give out some n-dimensional vectors that could be 2 digits, 4 digits, or any number of digits or numbers, maybe in different dimensions as well. And then when we compute the distances between images that are similar, the n-dimensional vectors, the distance between them should also be less. So the way it works is we use a specialized loss. It's called Triplet Loss, where you will have an anchor image, which is your target image for which you want to predict some vectors, and then there is going to be a positive anchor and the negative anchor. So the goal of our triplet loss is to basically quantify our image in such a way that when we compute the distance with the target image with the positive anchor, the distance should be as much less as possible, and then when we compute the distance of the target image or anchor image with the negative anchor, then the distance should be large. So this way it helps our model, classification model basically, to generalize in a way that whenever we put in some images which are similar, the quantifying vector which comes out of the model, if we do it for multiple models and then we compute the distance, so the distance between the vectors which are for similar images should be less, and then distance between the vectors which are from two different images should be high. So based on that we can create some indexes, and that could be used as a database to search for some labels. For example, a good use case for this is facial recognition. So here you can see on my screen. So usually on most of the online demos, people usually what they do is they'll generate some APIs from the Kaggle so that they can download a dataset easily. But I think that is a long way, and if you're just doing experimentation, that should be an easy way to download datasets. So here is a link for Kaggle dataset that you can go through. So I'll just open this link. Yeah, you have to be logged in to be able to see this download button. So once you click on this download button, it will just start downloading, and then if you hit Ctrl J on Chrome, you should be able to get this link. So if you copy this link address, I'll just cancel this download, and then here you just have to replace this one with the fresh link that you created, because it contains the auth token which would allow you to download the dataset. Alright, so now that our dataset is downloaded, let me remove the output. So we can unzip the archive zip which we downloaded from Kaggle, and then we can move it to dataset directory. Okay, so with that our extraction has finished. So again I'll just remove the output of this cell, so we can go into the dataset directory. So here the images are in the train, test and validation directory. So let's go to test directory. So each directory contains the classes, and then inside each class there will be some sample image. So we are doing bird classification here, so all of these will contain bird class. So all in all there are like 100 classes of birds that we need to recognize. So another important thing is, if you are working on your own dataset, just make sure that the number of classes should be equal in all the sets. So you cannot take random splits. You have to make sure that in each of the train, test and validation set, the number of classes should be same or equal, and then inside those classes you can have similar amount of images for each class to make this model perform the best it could. Alright, so we have seen our dataset, so let's move forward for the training part. So before that, I'll just quickly go through the model. So here we are using AlexNet, which is the pre-trained model from Pytorch repository, or we can say from Torch Vision module. So here we are inputting Torch Vision, and then inside the model we are using torchvision.models.alexnet. We can initially set the pre-train equals to true to start off from some weights, and then in the classification part, this is a fixed number based on the AlexNet, but if you plan to use some other architectures, you just need to change this model part, and then you can get the input features from the model by printing out the model and then replacing it with that. And then this embedding size is basically the m-dimensional embedding vector which you want your model to output for a given input image. Also, the input size is 128 here, so that means our model is going to take image with input size 128, and then it is going to give you 64 dimensional vector which is going to quantify the image. So if you take the images from same class and then compute their embedding vectors, you will get 64 n-dimensional vectors for both of those images. And then if you try to compute the distance between them, it could be Euclidean distance or cosine distance, you'll see it will have a smaller distance. However, if you take an image from a different class and then compute their distances, you will see that distances are high. And ultimately, this distance computing method is what we are going to use to build our indexes, and then use those indexes to find similar images or just labels for the input image. So with that, let me just execute this import statement. So we're going to use AlexNet, and then we have our some utility functions inside this utils. So for example, to build the DataLoader, we have this utility function, and then inside the common we have some other utility functions for computing the accuracy or computing the embeddings at once for accuracy. Again, we have some constants defined here, that is image size, batch size, or embedding size is basically the output. So I'm using a V100 GPU here, so I can accommodate 1024 images in a single batch. However, for you, if you have a smaller GPU, if you don't have enough memory, you can just try to reduce the batch size. So with that, I think we're good to go. I already put the path to train and val datasets, which is inside the dataset directory, so I can execute them as well. And later on, if you want to port this model, export this model to some other extensions, you may need pre-processing functions. So in the same utils directory, if I go to dataset, during data building, you can see the mean and std are predefined, and I'm not overriding them during function call because I think these are the best mean std from the ImageNet, so I'm going to use those. So in case if you want to do pre-processing manually, you can get those values there. So with this, our data loaders are ready, and then I'm going to define the instances for our devices, models, and then some utility functions which will be required for training. So for example, here we are initializing our AlexNet model, and then I'm also setting pre-train to true just to make sure that the training goes smooth with the pre-trained weights. And then we are simply using Atom Optimizer here and some additional functions, for example, distance, which is going to compute the cosine similarity for our images. These are all going to be used for retraining. And then finally, the losses. So this losses comes from the Pytorch Metric Learning repository, and then we're using triplet margin loss. I'll put some links in the description as well if you want to learn more about how triplet margin loss works. But at the end, these are the utility functions which we're going to use to train our model. So again, we are setting the epoch to 300, and then there is a history variable where we're going to save the overall training history so that we can visualize it later on. And because we are running it in a Jupyter cell, so sometimes what happens is if you restart the notebook or if you close the browser tab and then you come back, you might not be able to see the cell output. So in that case, we are also logging the whatever we print on the screen to a text file so that we can later use tail or some other utility command line tool to read and then see what's going on. So I'll execute this cell as well. And so finally we are on to the training loop. So it's very simple. We are first of all moving our model to GPU, setting it to train mode, because we are also setting it to eval mode for evaluation. So it's important that we make sure that the model is in training mode. And then we are iterating on the data loader to get the batch of data and labels. And finally setting 0 grad. And then here we are computing the embedding by passing our data to the model. And then there is a special function called mining function, which takes our embeddings and labels to find the samples which are good and bad. So for example, in the triplet margin loss, you need samples which are close to each other and samples which are different to each other. We need both of these kind of samples so that our model generalizes well in finding the difference between different classes and then similarity between similar classes. So here our mining function is basically trying to help us in the training by mining the pairs of those triplets. I mean by finding the triplets of the positive and negative anchors, and then we are passing it to our loss function, and rest of all the steps remain same. So you can those are standard for any Pytorch training model. So without any further ado, let's start the training. And I think I did not executed this cell. So let me initialize the models and then I can start the training. Okay, so the training has started, and initially you can see the loss is quite high and also the triplet. So these triplets are your best friend if you want to see how well your model is performing. So for example, in our case, the data set, we have, let's say 50 images per class. Okay, so that means in maximum, if our mining function is finding the triplets, the number of triplets that it should find for each class, maybe it should be somewhere around those 50 to 100, because we are also using negative anchors. So the lesser this triplet number goes, the better our model is performing. So you can see immediately after a second iteration, it has jumped from 96 1325 to 29 1454. I mean, these are huge numbers, but you can see that triplets are eventually going down. So it will take some time to train and then to evaluate the model. So what I'm going to do right now is I'm going to just stop the model and then bringing the weights from previous training and then just do a evaluation to see how our model is performing, and then we can move forward to visualize our models and see the predicted outputs. So I'll just stop this training for now, and here this is an additional step. If you also want to restart your training from a previous weights, you can do that. So I've saved this previously trained weights into the previous directory. Okay, maybe not. So I think I already have this model best, so I may need to rename this. Alright, so we have loaded our model, and now instead of training it, we can just evaluate our model. So in order to do that, I'm going to copy this part into a new cell. For now, you don't have to do this. It will just do automatically in the training loop. So let's just do that. Okay, so while this is evaluating, I also want to highlight this one thing. So during evaluation, what I'm doing is it computes the accuracy, and then it checks the current accuracy with the best accuracy that might have happened in the past, and based on that it stores the model best. So we are not storing the weights for each and every epoch. We are only storing the latest epoch, and the model best is only going to be updated if you have a higher accuracy than previous evaluations. So we can be pretty comfortable that if you use the model best, it is going to give us the best results. So right now we are evaluating the model best.pth saved weights to see the accuracy for that weight file that we trained previously. Okay, so the results are out. So I think it is around 88%. So that should be good enough, given that we only trained it for like 100 epochs maybe. So I think the evaluation is complete, and our model, although I didn't actually study the training, but I have already previously trained it. So we can use this weight file to do our visualization. So let me come back here. So when you will train the model, you will see there is also a history.json file which is logged in between the evaluation loops. So what you can do is you can use that JSON file to compute your loss function. By the way, this is a different independent notebook, so you can also do it during the training, and the precision graphs. So these are from previous runs. So at 8.75, what you got there is the same thing which we are getting right now. So moving forward from there, let's talk about the model predictions. So I'm going to import the same things which we did in the previous notebook because we want to load our model. And so here, instead of using the default data loader from Pytorch, what I'm doing is I'm manually defining the transform function and then passing in the value for mean and standard variations. And I think I have to pass the image size as well, which I haven't. So image size is going to be 128. All right, so let's define this, and then okay, so it was already defined here. Nice. Anyhow, so we're going to what we're going to do is we will take the images from our validation set, compute the embedding vectors for the validation set, store it into some dictionary, so, and then later for each query image from our test set, we will compute the distance between the current query image and its query embedding vector with the all the vectors will be stored for the val set, and the closest match we can find, we will just print its label and then also plot the image for that. So I think I need to change the path of the model, so it's going to be model best. So we have our trained model loaded into the memory, and instead of loading the image one by one, and because we are not utilizing the Pytorch data loader, so this is a simple loop which loads the images into batch and then pass it through the model, and then for each image it stores the embeddings into the dictionary. So this is computing the embeddings for now, and I think I can have a look at the dictionary. I think it's very large, but we should be able to print that. Okay, so the 0 key here is basically the index of the images in the validation data set, which we will later on use to refer to and then get the labels back, and this is the embedding vector for that particular image at that index. So we have the index for all the images in the validation data set in our memory. Now I'm going to load some images from our test set, and here we are choosing the randomly 5 images from our test set to evaluate, and after that this is our prediction. So basically in this step what we are doing is we are finding the distance between the query embedding, which is the embedding for the image which we just loaded from our test set, and the embeddings which we have already indexed in our previous step. And out of all these embeddings, whatever the distance, the lowest distance with which we can find that embedding, we get the index for that particular embedding, so that here in this step we can find the predicted label from val set, and then the actual label can be directly inferred from the path of the image, because the way dataset is structured right now is the directory name which contains the class name is going to be your label, and then for each class name we are going to have the images for that class. So we can pretty easily use that to get the actual label, and then predicted label can be taken from the index which we predicted later on. So with this you can clearly see that this is the query image which we loaded from our test set, and out of all the images which we indexed from our validation set, this is the closest match that we could find. So you can also see the labels. So this was the actual label for the image, this is the predicted label. As you can see, the images are completely different, but we are able to find the exact match for that image. So all in all, we can say that our metric learning has learned to understand the image, the structure of the image, and then quantify it in such a way that we can find the closest matching image for that particular image. So this is part 1 of the metric learning. In the part 2, we are going to see I'm going to explain how we can utilize this model to build a indexing pipeline which can be used to run the model in real time, so that whenever we have an input image, we should be able to get some matching image or also the label of that particular image. So I know you can say that we can use classification model for this task as well, but in the long run, when you have more classes and less number of examples, you should avoid classification. Instead, going with metric learning and then using some indexing is a good way. And also you don't have to train the model again and again. Instead, what you can do is you can basically update your index, and then because your model already understands how to quantify different classes, if you have new images, you can just update your index, and then your pipeline should still work without retraining the model. So every model will have its use case, but I think it's important that we go through these things and then understand the concepts. So all these links to the code that I'm working on here, you can find it in the description below. I'll add the link for the GitHub repository. You can take from there. So that was all for this video.